What's up, Honors Math 3? Super excited to be teaching you guys today. Mr. Shane's been doing the past couple videos, so I figured I'd jump in. And today we're going to be talking about solving logarithmic equations, right? So the past couple days we've been doing a lot of practice with logs, right? We've been transforming them from logarithms to exponential form. We've been solving exponential equations, and we've been just doing a lot of log properties. And today we're going to kind of learn more about how we're going to apply that, right? So let's talk about these learning targets. Right, the first one is I can solve a logarithmic equation by switching it to exponential form. Right, so we've been doing a lot of that, transforming log functions to exponential functions and vice versa. So today we're kind of going to use that to solve some equations, right? Number 13, I can solve an equation by setting two logarithms equal to each other that have a common base. Right, we kind of did that the other day in our skill builders, except it was the exponentials, right? We had exponentials with the same base, so we used that to solve the exponents, right? And number 14 here is I can use the properties of logarithms to help simplify an equation and make it easier to solve, right? So we just learned about the properties of logarithms, and today we're just going to apply them to solve equations, right? So if we're looking at method 1, switching to exponential form, what that means is that we're going to use kind of that transformation to make it easier to solve, because sometimes it's easier to solve it in exponential form and sometimes it's easier to solve it in logarithm form. Right, so if we're looking at this example here, right, it gave us log base 6 of x plus 5 is equal to 2. Right, so here, because we have our variable inside of the logarithm, it might be a little bit easier to switch it to exponential, right? And we can do that so that we can isolate that variable, right? So we can rewrite this using our transformation, right? Here's our base of 6. That would be 6 squared is equal to x plus 5. All right, and now this just becomes a simple equation, right? 6 squared is just 36 is equal to x plus 5. All right, we can subtract that 5 over, and we end up getting x is equal to 31. All right, so that's just a good example of how it might be easier in certain cases to just switch to that exponential form, so that we can solve for our variable. All right, so method 2, setting logarithms equal. Right, and what we're trying to do here is we're saying, okay, well, let's say we had an equation like this one, right? Log base a of m is equal to log base a of n. Well, because these are both log base a, right, what we can do is we can just say, well, then m has to be equal to n, right? They have to be the same number. And remembering our domain, right, we have to remember that m, n, and a all have to be positive numbers, and a cannot equal 1. Right, just because we can't have a 0 or a negative inside of that logarithm. Right, so the goal in these problems would be to have the same base so that we can just set what's inside the logarithms equal to each other. Like number 2, right? Here we have log base 3 and log base 3. So we know, okay, well, we can just kind of drop those, right? We can get rid of these log base 3's and we can just say x minus 7 is equal to 3x minus 25. And again, now this is just kind of an algebraic equation that we can solve, right? So we can kind of subtract this x over. We get negative 7 is equal to 2x minus 25. Right, we can add the 25 over, and we get 18 is equal to 2x. All right, we can divide that 2, and we get x equals 9. All right, and a good kind of habit to get into is to try to plug in this into your log to make sure that we still have a positive number here. So, right, 9 minus 7 is 2, so we got a positive number there. right? 3 times 9 is 27, minus 25 is 2, so we're good there, right? And that'll kind of come and play in some of our later examples, but it's just a good habit to get into. Right here, we have a very similar problem, right? They're all log base 2, but now what I have is I have log base 2 of 2x minus log base 2 of x minus 2 equals log base 2 of 3, right? So I got to find a way to combine these two so that it's just 1 log base 2 of something is equal to this log base 2 of 3, right? And luckily, right, we can think back to our properties of logs. Right? And remember, if I have log base 2 minus log base 2, and if you look at the bottom of this here, right, if we have the same base and they're being subtracted, we can rewrite that kind of as a fraction, right? Which we have an example of it right here. Log base a of m minus log base a of n, we can rewrite that as log base a of m over n. So we can just rewrite this as log base 2 of 2x over x minus 2, right? And now, since we have the same base on both sides, right, and there's only one of them on each side, we can kind of just drop that base. And we get 2x over x minus 2 is equal to 3. All right, so then we can kind of multiply this x minus 2 over, and it becomes 2x is equal to 3 times x minus 2. All right, and I'm going to kind of draw it up here a little bit. All right, we can distribute the 3 inside the parentheses, and we get 2x equals 3x minus 2. Sorry, minus 6. And then what we can do, we can subtract this 3x over, which gives us negative x equals negative 6. And then we can just drop that negative. We get x equals 6. Right, so that's a good example that's going to kind of bridge us into the next part, which is using the properties of logarithms first, then change to exponential form. Right, so we have our logarithm properties, and we're going to kind of use these to give us a better chance of solving equations. All right, so let's look at some examples. Okay, so here we have 2 times log base 3 of x plus 4 minus log base 3 of 9 equals 2. Right? And we're not going to be able to set the logs equal to each other because we have this 2 here, right? So we can't try to get rid of the logs. But what we can do is kind of use our properties of logs and then kind of transform it into that exponential equation so that it's a little bit easier to solve. Right? So the first thing I have to do is I have this 2 on the outside here. And I got to bring that inside of this logarithm so that I can use my property of the logarithms that are subtracted by each other, right? So if I look here at my properties, right, if I have a coefficient outside of the logarithm, right, I can just bring it as an exponent inside the logarithm. So this 2, I'm going to bring it to the exponent inside of the logarithm. So this becomes log base 3 of x plus 4 squared, and then minus log base 3 of 9 equals 2. Right, so now I can use my property that we used earlier and say, well, that's just going to be log base 3 of x plus 4 squared over 9 equals 2. Right, and now this is something I can transform into exponential form, right? I can say, well, base of 3 squared is equal to x plus 4 squared all over 9. Right, and 3 squared is just 9. If we multiply this 9 over, 9 times 9 is 81. And that's going to be equal to x plus 4 squared. And what we can do here now is we can take the square root of both sides. Because, and I'm going to rewrite this right here, square root of 81 is 9. And the square root of x plus 4 squared is just x plus 4. And from here we can say, okay, well then x has to just be equal to 5. Right, which makes sense. So for number 5 then, what we can do is we can use our property of addition, right? If we have two logarithms that are being added together, right, we can just say, oh, well, bring them inside the same log and multiply them, right? So we have log base 5 of x plus 3 plus log base 5 of x minus 1. Well, we can just rename that log base 5 of, and let's give some brackets here, x plus 3 times x minus 1. And that's equal to 1. Right, and now we can rewrite it as an exponential because, right, we have a base of 5 raised to the first power is equal to x plus 3, x minus 1. Right, and now what we can do is we can FOIL this out, right, because this is just 5 equals x squared plus 3x minus x minus 3. Right, I can subtract this 5 over, and I get 0 equals x squared. I can combine these two together, right? 3x minus x is just 2x, and then negative 3 minus 5 is negative 8. Right, I can factor this out because now I'm just trying to solve for 0, right? So I want to know what x can I plug in to give me 0. Well, if I factor, it makes it a little bit easier, right? Because I can say, well, this is the same as x plus 4 times x minus 2. Right, now if either of these end up being 0, then I have a 0 as the whole equation. So I can just set them equal to 0. Right, I can say, well, and let me bring it up here real quick. I can say, well, x plus 4 equals 0. That'll give me x equals negative 4. Right, the problem with this, though, right, is if I plug this into my log, it's actually going to give me a negative number inside my logarithm. Right, so I can't have negative 4 as my answer because it doesn't work in the domain. Right? But what about this x minus 2 equals 0? Well, that's just x equals 2. If I plug in a 2, that gives me a positive number in my logarithm. So I know my answer then is just x equals 2. Right, so let's look at a couple more examples here. Here we have the natural log of x plus 3 equals 2. Right, and this is just a good one to remember that the natural log, well, that's just log base e of x plus 3 equals 2. So we can put this in exponential form, right? We can say e squared is equal to x plus 3. Right? Then all we would have to do is subtract 3. We can say e squared is equal to, e squared minus 3 is equal to x. Right? And this we can just punch into our calculator, right? Because e is just a value, it's a constant. Right? So if we just plug in e squared minus 3, right, we get this 4.3890, and it just keeps going. So we can say x is about, right, because we're going to round it off a little, 4.389. right? Number 7 here, it gives us two log functions with the base of 5, right? But the problem is we have this coefficient out front. But the good news is we remember our properties, right? We can just bring those coefficients to the exponents inside of the logarithms, right? So this just becomes log base 5 of x squared equals log base 5 of 4 raised to the third power, right? Now we have two logs that have the same base, right? So we can kind of just drop the logs and we can say x squared is equal to 4 cubed, right? Well, 4 cubed is it's just 64, right? So now we have x squared equals 64. We know, oh, we just got to take the square root, right? And what's important to remember here is that when we take the square root, we're going to get x is equal to plus or minus 8. But because of our domain, right, we can't have a negative number inside of our log, right? So this negative is not going to work. So we actually just have x equals 8. All right, number 8 over here, we have log of x is equal to 2 minus log of x minus 21. And if we remember, if there's no base written, right, it just means it's log base 10. Right, so here we're going to have to do some algebra. We have to move this log to the other side to get them together, right? Because we're going to have to use our properties to combine them. So if we add this log of x minus 21 over, we get log of x plus log of x minus 21, all equal to 2. Right, then we can use our properties and combine these. Remember, if we have logs that are being added together, we can just multiply what's inside of them, right? So this becomes log of x times x minus 21 is equal to 2. Right, so now what we can do is, because this is log base 10, right, we can just put it in exponential form. We can say 10 squared is equal to x times x minus 21. Let me scoot this down a little bit. Right? And now we can kind of simplify this a little bit, right? 10 squared is 100. X, we can distribute that inside the parentheses here. We get x squared minus 21x. Right, and now we can kind of see, oh, this is going to be a polynomial that we have to set equal to 0, right? So we can subtract this 100 over. We get 0 equals x squared minus 21x minus 100. Right, and now just like the problem we did earlier, right, we can just factor and figure out what values of x I can plug in to get 0. Right, so if I factor this out, I'm going to get x minus 25 times x plus 4. Right, and now I just have to set these two expressions equal to 0. So I have x minus 25 equals 0, which means x equals 25, which fits in our domain because it's a positive number. And then we have x plus 4 equals 0, which would give us x equals negative 4, which does not fit in our domain because that'll give us a negative number inside of our log here, so we cannot use this one. All right, so our answer then would be x equals 25. The last one here, right, we have 3 plus 4 natural log of 2x equals 15. Right, so what we can do is we can subtract this 3 over, and we would just get 4 ln of 2x is equal to 12. And we could use our properties of logs, right, and bring this 4 to the inside here, right? But we could also just divide the 4, right? because this is going to cancel, right? And I get ln of 2x is equal to 3. Right, so sometimes we got to remember it might just be easier to kind of use our algebra skills rather than using the properties. We could have used the properties, but this just kind of made it a little bit easier, right? And so natural log, if we remember, is just log base e. That's going to be 2x is equal to 3. And now that we have it written like this, we can write it in exponential form, right? We get e cubed is equal to 2x. Right, we can divide this 2 over, and we end up getting e cubed over 2 is equal to x. Right, and we can just, again, plug that into our calculator. Right, we get e raised to the third power divided by 2. Plug that in, we get 10.0427, right? And we're going to round it off again. So we can say x is approximately 10.043